So welcome. We are going to be going over how to do this lab. The first thing you need to do is, well, read the instructions. That's always a good place to start when you're trying to figure out how to do something. So you're going to load that lab. You'll open it up. You're going to start with the fire extinguisher force at 200 newtons, and then you're going to determine the mass that you use based on the first letter of your last name. So whatever that first letter is, it will tell you which kilograms to set it to. You'll use the same mass for every trial. Then you're going to start the simulation and stop the force as close to 4,000 milliseconds as possible. When I run that simulation, you'll be able to see exactly what that looks like. Then you're going to record the extinguisher force. It will have been set at the beginning. You kind of get to pick it. You start at 200 and decrease it by one tick each time. You will also record the force time, that actual time, not 4,000, whatever you actually stopped it at. The distance between the photo gates is always 10 meters. The photo gate time, which will be dependent upon how fast you're moving. And then Wally's mass, which does not change either. So you're going to decrease the extinguisher force to 190 and run the simulation again. You're going to continue to decrease the force by one click each trial until you have, instead of 11, we're doing 7. So 7 sets of data. And it doesn't go to 50, it'll go to 100. All right. In order to find the momentum, when you get to that point, I'll show you that. You'll use that equation. In order to find the impulse, when we get to that point, I'll show you, you use this equation. So your first data table looks like this right here. You've got extinguisher force, force time, distance between photo gates, which is 10 meters all the way down. Photo gate time, that'll change each trial. Wally's final speed will be the distance between the photo gates, 10 meters, divided by however long it took to get between those two posts. So it'll be 10 meters divided by the photo gate time of that trial. Wally's final speed will be dependent upon that, but his initial speed is always 0. He starts from rest in every scenario. And then this final column is the mass. You'll determine that before you ever start, and it'll be the same for each trial. So if you notice right here, there's a little tick mark on the 7th row. I'd suggest you do that just so you don't take more data than you need. It would just make the graph that much more accurate, but it will save you time to just do 7. So what I'm going to do now is I'm going to switch over to the lab, and we're going to do exactly that. I'm just going to use the preset 70 kilograms. Yours will be dependent on your last name. So the first thing you want to do is turn up the fire extinguisher force all the way. It maxes out at 200. And then you're going to hit activate. The force time starts as soon as you hit activate. You're going to try to stop it as close to 4,000 as possible. So I didn't really hit stop it there, 4,000, but it was pretty close. The limitations I suggested is within 100 milliseconds. I missed it talking there. But you might have to try it a couple times like this. That would be a applicable trial there because it's within 100 milliseconds. So the data that you're recording from each trial is the extinguisher force. Remember that you'll decrease it by one click each trial. The force time, that'll be dependent on how accurate your clicks are. But you still want it within 100 milliseconds of 4,000. And then the photo gate time. So you'll take those values. I've got 40, 50, and 88.5. So my fire extinguisher force is going to be 200 newtons. You don't need to put the units because the units are labeled as part of the column. The force time was 4.050. Remember to divide the milliseconds by 1,000 in order to get them in seconds. That's why there's a decimal point after the 4. The distance between the photo gate is always 10 meters. The photo gate time was 885. So that's going to be a 0.885. All right, because 885 divided by 1,000 is 0.885. The final speed will be dependent upon those two. We'll get to that in just a second. The initial speed will always be 0. You can fill that in for all 7 trials up front. And I use 70 for mine. Yours might be different. So my suggestion is collect all data first. Go back and calculate the final speed. Then once you have the final speed, do the second chart. So let's go ahead and look at that. I'm only going to do one trial. So I'm going to go ahead and calculate my speed so that I can then use it in the second part. That speed is going to be the photo gate distance, 10. divided by the photo gate time, which will be different every trial. So 10 divided by 0.885 will give me 11.3. So I'm going to use 11.3 meters per second for that trial. Now, this data will inform the next chart on the next page. So you go down to the next page. There are 4 columns. The final momentum, well, the statement up here states that momentum is equal to mass times velocity, and that will be final velocity. Final velocity for my trial was 11.3. My mass is 70. So in order to find the final momentum, I'll have 70 times 11.3. And that will give me 791 kilogram meters per second. Okay. Then Wally's initial momentum is dependent on the initial velocity, which was, he was at rest. So that's 0. 0 times 70 is 0. So if you start at 0 and you end at 791, that means the change in momentum is 791. So you're really only doing math for the first column of the second chart and the last column of the second chart. The initial momentum will always be 0. The change will always be the final, okay? That'll be really easy. You just have to fill it in. Now the impulse here, if we roll up to determine how to solve for impulse, J is the letter we use for that because I is already taken, but it is force times the time over which the force was acting. So that'll be force time. That's the first 2 columns of your first chart. So this, for me, will be 200 multiplied by 4.05. All righty. So that's going to give me 810. What's that?
Did you say the force time we're doing?
Yes, force times force time. All righty. So you're going to notice that you should see values kind of close. They won't be exact. It'll be dependent on the accuracy of your calculations and your measurements, but you'll have to work with what you got. All right, that's how you fill out this chart. This chart is where you get your graphing information from. The last 2 columns are what you graph. So while we're looking, let's go ahead and show you. I know you may not be there yet, but I suggest you watch so that when you get there, you know how to do it. All right, so on this graph, you want to put impulse on the y-axis. You want impulse right here. You want momentum on the x-axis. It really doesn't matter, but I'm just going to go ahead and clarify it for you because sometimes indecision or indecisiveness will paralyze you. All right, so we've got impulse versus momentum. That's what the graph is called, so that's why it's y versus x. All righty. Then you're going to plot your data points. I will warn you, something you might notice is that your first values will be your highest. So one of the trends you're going to notice is that the values for impulse and momentum will decrease as you go from top to bottom. So when you graph this, it will look like you're graphing it backward. For instance, your first data point, let's just say you max out your data over here, will probably be somewhere over here. That second data point will be somewhere to the left and below it. All right. So it's going to look like you're graphing backward. I don't want you to think you're doing the wrong thing. The data starts like higher values and works toward lower values because you're decreasing the force. So impulse has to go down as force goes down. Okay. So, and you're trying to keep the time as constant as possible. So if T stays constant, F goes down, impulse goes down. So you're going to see those values decrease. So you're going to graph from right to left. I know that feels weird. And then the final idea is, well, you're going to have to determine the slope. The slope is the final value here minus the initial value there. So generally, if you remember the formula for slope, it's y2 minus y1, right? That's for increasing data sets. Does that make sense? So really what you're looking at is you're looking at this value over here. That's going to be y1. This will be y1, x1, this data point. This data point down here will be y7, x7. Does that make sense? It'll be the 7th data point. So you're going to take the first data point and subtract the 7th data point from there. So maximum minus minimum is really what you're doing here. Okay. So when you do that, it'll be y1 minus y7 because it'll be the 7th trial. That's the second value there. And then you'll do that over x1 minus x7. Okay. So this will be impulse over momentum. You'll get a value. So something I wanted to show you here, because you will not analyze the dimensions of units well enough to notice this. Impulse is your y-axis. So the units for that are newtons times seconds. 1 Newton is a kilogram meter per second squared. And then you multiply that by seconds to get impulse, because it's force times time. So that's in your numerator. In your denominator, you have kilograms, which is mass times velocity, which is meters per second. So you've got kilogram meters per second squared times seconds over kilogram meters per second. I want you to notice when you multiply the newtons by seconds, what happens to this square in the denominator? It goes away. And this becomes, I'm going to do this in a different color just so it shows up as I pick the brightest color possible. Kilogram meters per second over kilogram meters per second. What do you notice there? What's going to happen? What do the units do? They equal 1. So the units cancel. There are no units for your slope. That's indicative of what this is supposed to be representing. Maybe you can go ahead and recognize it. All right. The value will be a number. It will approximate a number. You'll be either on the positive or the slightly less than side, but it's going to approximate a number. It is supposed to be that number. You'll recognize it once you calculate the slope, and it should make sense. What are we trying to prove here? I just want to remind you, what's the point of this lab? Impulse momentum theory states that impulse is equal to what? What did we learn yesterday? To the change in momentum. What are you graphing here? Impulse versus change in momentum. This is why the units cancel. So your magnitude will be a number. Your units, you will have none. I don't want you sitting there 20 minutes trying to figure out how the units cancel. All right? They are completely gone. What's the physics equation for your graph? We just stated it. Impulse equals momentum. What does the equation represent, and what's the name of this equation? And that's the if you need for more information, there's a link up here. So that's the Impulse Lab. There's a link right there that will help you answer that question if you need it. But hopefully you know that I just said it. It's a theorem. It's what you're trying to prove here. Then when you get to number 6, the equation for momentum, it's given on the lab. You don't have to go anywhere. It's up there. I already showed it to you. The equation for impulse, also given on the lab. What's the relationship between impulse and momentum? Well, that's the impulse momentum theorem, all right? So you should be able to state that, and if you need help, you can either ask me, which would be a great idea, or you can click on that link to find out, all right? And then you're done with the lab. You should hopefully already be done with data collection. At the very least, you definitely should have started. At this point, I'm going to stop the recording because no one needs to have a recording of me lecturing you.